This is the explanation for the power series Meaty problem by Brian S., Kenny Z., and Ruchira H. Okay, so let's go over the givens first. What we're given is that f of x is equal to negative cosine of x squared divided by 3, and that g of x is equal to 3 f of x plus 1 divided by x to the fourth. Finally, we're given the fifth derivative of f of x, and it is shown on the interval of negative 1.25 to 1.25 closed brackets. So the first thing that we need to do, or part A, is to find the Taylor series representation of f of x. And we want to use this to find the Taylor series representation of g of x. So the way to find the Taylor series representation of f of x is use the Taylor series representation of cosine of x, which is the summation from n is equal to 0 to infinity of negative 1 to the power of n multiplied by x to the 2n divided by 2n factorial. And if we're going to represent cosine of x squared as a Taylor series, we're going to replace the x here with x squared. So our representation of cosine of x squared is going to be the summation from n is equal to 0 to infinity of negative 1 to the power of n multiplied by x to the 4n divided by 2n factorial. But this is not all of f of x. F of x is negative cosine of x squared divided by 3, so we need to go ahead and multiply this series that we found here by negative 1/3 to get the final series of f of x, which is going to be the summation from n is equal to 0 to infinity of negative 1 to the power of n plus 1 multiplied by x to the 4n divided by 3 times 2n factorial. Okay, so part A of the problem also tells us to use the Taylor series representation we found here to find the Taylor series representation of g of x. So I split g of x up and I wrote it as 3 f of x divided by x to the power of 4 plus 1 divided by x to the power of 4. So we can rewrite 3 f of x divided by x to the power of 4 using this Taylor series representation here as the summation from n is equal to 0 to infinity of negative 1 to the power of n plus 1 times x to the power of 4n minus 4, because we're dividing by x to the 4 here, divided by 2n factorial. That 3 that was previously here has gone away because we're multiplying this f of x by 3. Okay, so when we write out this component of g of x as a summation, or as like a series with several terms, we're getting negative 1 over x to the power of 4 plus 1/2 ... So when we add 1 over x to the power of 4 to this series, the negative 1 over x to the power of 4, which is our 0th term, cancels out with that 1 over x to the power of 4. This means that our series for g of x is going to be this series that we found right here, but starting at the term n is equal to 1. This is because that 0th term ended up canceling out. So our final Taylor series representation of g of x is going to be the summation from n is equal to 1 to infinity of negative 1 to the power of n plus 1 multiplied by x to the power of 4n minus 4 divided by 2n factorial. If we wanted to start this polynomial at n is equal to 0, which will be useful in part B for this problem, we would rewrite it as negative 1 to the power of n plus 2 multiplied by x to the power of 4n divided by 2n plus 2 factorial. This method of splitting up our fraction into two parts and canceling out the 0th term is pretty common when you see functions in this kind of style with two terms added in the numerator and a common denominator, and we're asked to find the Taylor series of that function. So that's all of part A. Now let's go on to part B. So part B asks us to find the Taylor series representation of g of x minus f of x and the 8th degree Taylor polynomial that represents this. So what we want to do is subtract g of x minus f of x, and since at the end of part A, I represented g of x as starting at n is equal to 0, we can just straight away subtract these two power series representations. A common error is subtracting the two power series representations, but not changing g of x to start at n is equal to 0. When we want to subtract the two power series representations, we want to make sure that both of them are starting at the same term number, which in this case is n is equal to 0. So what I realized when I was subtracting these two fractions here is that there are several common factors between the two fractions. So I went ahead and I factored those out. So then I got negative 1 to the power of n plus 1 times x to the 4n divided by 2n factorial. These were the common factors that I saw. And then I had that multiplied by negative 1 to the power of 2n plus 1 times 2n plus 2 minus 1/3. Even inside this parenthesis here, I saw another common factor of negative 1, so I pulled that out of the parentheses to get the final summation of g of x minus f of x, which is the summation from n is equal to 0 to infinity of negative 1 to the power of n, which is the same thing as negative 1 to the power of n plus 2, multiplied by x to the 4n divided by 2n factorial, multiplied by 1 over 2n plus 1 times 2n plus 2 plus 1/3. The other part of part B tells us to find the 8th degree Taylor polynomial that represents this. So we want to go ahead and plug in n is equal to 0, n is equal to 1, and n is equal to 2 into this Taylor series representation, because when we plug in n is equal to 2, we get x to the power of 8, and that's what we're looking for, right? We're looking for the 8th degree Taylor polynomial. So when we plug in n is equal to 0, this term goes to 1, and this goes to 1/2 plus 1/3. When we plug in n is equal to 1, we get negative x to the 4th divided by 2 factorial, multiplied by 1/12 plus 1/3. And when we plug in n is equal to 2, we get x to the 8th divided by 4 factorial, multiplied by 1 over 30 plus 1/3. And then we stop plugging in values with n because we've gotten to x to the power of 8, and we're looking for the 8th degree Taylor polynomial as mentioned previously. Now what I'm going to go ahead and do is simplify this whole entire term here. So this becomes 1/2 plus 1/3 becomes 5/6 minus x to the 4th over 2 multiplied by 5/12 plus x to the 8th divided by 24 multiplied by 11 over 30. And the final thing I'm going to do is just multiply straight across to get 5/6 minus 5x to the 4th divided by 24 plus 11x to the 8th over 720. And that's going to be the final 8th degree Taylor polynomial that represents the power series of g of x minus f of x. So that's part B done. Now let's go on to part C. So what part C asks us to do is to use the 8th degree Taylor polynomial found in part B to approximate the integral from 0 to 1 of g of x minus f of x, and that integral represents the area between the two functions on 0 to 1. Okay, so we know that we have the 8th degree polynomial of g of x minus f of x found in part B. It's going to be 5/6 minus 5x to the 4th divided by 24 plus 11x to the 8th divided by 720. So now what we're going to go ahead and do is we're going to integrate that g of x minus f of x from 0 to 1, because that's exactly what part C tells us to do. So when we're integrating a function, we have to find the respective antiderivatives of each component and then plug in the upper bound and subtract the lower bound from that. So we get 5/6x minus x to the 5th divided by 24 plus 11x to the 9th divided by 720 times 9. This is just using the integration power rule. And our bounds, of course, are from 0 to 1. So when you plug in 1 into each respective antiderivative component, you get 5/6 minus 1 over 24 plus 11 divided by 6480, or 6,480. And if we were to subtract 0 from that, plugged into all the antiderivatives, that would just be 0, because each antiderivative component has an x term. So our final answer for the integral from 0 to 1 of g of x minus f of x is going to be 5/6 minus 1 over 24 plus 11 divided by 6,480. Since this component of the problem is no calculator, we can just leave the fractions in this manner. Okay, so for the final part of this problem, we need to find, or part D, we need to find the maximum error using the 4th degree Taylor polynomial for f of x to approximate values of f of x on the interval 0, 1.25. So since this problem says we need to use error, we are probably going to end up using the Lagrange error bound. So this is the general form of the Lagrange error bound. It is the absolute value of m, representing the maximum value of the n plus 1th derivative, multiplied by x minus a to the power of n plus 1, x being the point furthest from the center and a being the center of the Taylor polynomial, divided by n plus 1 factorial. And in this case, n represents the degree of the polynomial in the approximation. So since the problem says we're using the 4th degree Taylor polynomial for the approximation, n plus 1 is going to equal to 5 since n is equal to 4. Okay, so we need the maximum value of the n plus 1th derivative, and that's the purpose of this graph here that we're given. Okay, so the error asks for us on the interval of 0, 1.25, so we might as well just ignore that left half of the graph and only focus on the interval from 0 to 1.25. We need to find the maximum value of the n plus 1th derivative. So a common error is just to say that that value is 0, but that's not true. That value is actually going to be negative 54 because we're taking the absolute value of it. And the absolute value of 0 is less than the absolute value of negative 54, sorry. So really, we're not just looking for the maximum value of the n plus 1th derivative, we're looking at the value on the n plus 1th derivative that has the maximum absolute value. So negative 54 will have a greater absolute value than 0 will. So that's why we're using negative 54 in our Lagrange error bound. And then we know that 1.25 is the furthest point from our center at 0, so we're going to do 1.25 minus 0 to the power of 5, and we're going to divide that by 5 factorial because, as mentioned previously, n plus 1 is going to be equal to 5. And then, since this problem is allowed a calculator, we will just plug this whole value into our calculator to get a final error of 1.373. And that's how we would find the error of this polynomial using the Lagrange error bound. That is all. Thank you for listening.